Back. So we were in the process of proving the L'Hopital's rule. Recall the rule. Suppose f and g are differentiable and g prime at x is non-zero on an open interval I that contains number a except possibly at a. Suppose limit x approaching a of fx is 0 and limit x approaching a of gx is 0, or limit x approaching a of fx is plus or minus infinity and limit x approaching a of gx is plus or minus infinity. Then limit x approaching a fx over gx, which would be 0 by 0 or infinity by infinity, it is actually equal to limit x approaching a of f prime x over g prime x. So that is, when you hit indeterminate forms of 0 by 0 or infinity by infinity, you may as well take derivatives. Okay. To prove this, we first needed to prove Cauchy's mean value theorem. If you have two functions f and g which are continuous on closed interval ab, differentiable on open interval ab, and g prime x is non-zero for every x in open interval ab, then there is a number c in open interval ab such that, okay, that was a mouthful. The quotient f prime c over g prime c is fb minus fa over gb minus ga. We proved this in our previous video. Now let's go to L'Hopital's rule, proof of L'Hopital's rule. So let's first consider the case when you have indeterminate form of 0 over 0, that is limit x approaching a of fx is 0 and limit x approaching a of gx is 0. Let L be limit x approaching a f prime over g prime. We want to be able to say that limit x approaching fx, x approaching a of fx over gx is the same L, that is limit x approaching a f prime x over g prime x. So you want to show this is equal to this, that is this is L. Now, what do you do? When x is not a, consider fx. When x is a, set it 0. Let's call this capital Fx. Likewise, gx. When x is not a, capital Gx should be simply gx, and at a it should be 0. Okay? So what do we say? Limit x approaching a of capital Fx is 0 because that's what f at 0 is. Limit x approaching a of capital Gx is 0 because that is g of 0. So notice, why are we making a fuss about all this? F and g was differentiable except possibly at a. Okay, go back to the statement. F and g are differentiable, therefore they are continuous. G prime's x is non-zero. Okay, except possibly at a. So at a, f and g may not even be continuous. G prime at a may be 0 for all you know. Okay, so this is why we introduce other two functions, capital F, capital G, which kind of smoothens the possibly lack of continuity. So I'm placing a 0 for value at a because that's the limit you have. So that makes capital F and capital G continuous because limit x approaching a of capital F is the same as the limit of little f, because for x not 0, capital F is nothing but little f. So I hope this is clear. So capital F and G are continuous. Now we want to understand what happens when I am to the right of a. Let x be greater than a and x be in your interval that you are discussing everything in. So limit your world to that small subinterval closed a to b, a to x. Capital F and capital G are continuous because, well, they were continuous on the bigger interval. So surely they are continuous here. What about differentiable on open AX? Of course they are differentiable. Why? Because little f and little g are differentiable on everything except A, but this interval does not have A. So capital F and capital G are also differentiable here. Moreover, G prime is not 0 because G prime is nothing but little g prime. You see, capital G is same as little g everywhere except A. And this interval does not contain little a, so it's same as G prime. Alright, likewise capital F prime is same as little f prime. So now you have two functions, capital F and capital G, continuous here, differentiable here. So we may apply the Cauchy's mean value theorem, which we just proved in our previous video. On this interval, what do we know? There is a number y between the endpoints such that capital F prime y over capital G prime y is the differentials at the endpoints, capital Fx minus capital Fa over capital Gx minus capital Ga. But Fa and Ga are 0. Alright, because at A, the values are 0. So all you have is capital Fx over capital Gx. In other words, remember my x was to the right of A. You see? So when I'm letting x approach A, I'm letting it approach from the right. Limit x approaching A from the right of the quotient little fx over gx is nothing but limit x approaching A from the right of capital Fx over capital Gx. But this is same as f prime y. Okay. So now note, as x is approaching A, my y is getting closer to A as well because y came from this interval. All right. So f prime is nothing but little f prime. Capital G prime is nothing but little g prime. And this limit is what we called L. As x approaches A plus, A from the right, that little y, which also is in that small interval, that also gets pushed towards A. So this limit is nothing but L. In other words, you got the right hand limit to be equal to L. So you wanted both limits to equal. So this is general limit, right and left. So you got right hand. Well, the argument is same. To say coming from the left, replace x greater than A by x less than A. Then you have interval x to A. I hope it's clear. So what you have here is A to x. If x were less than A, you would have x to A, x to A, x to A, and so on. All right. So I don't need to write it down again. But the argument is same. Left hand limit will also be equal to L. Right hand limit, left hand limit agree. So limit x approaching A, fx over gx is L. So this proves L'Hopital's rule when you are approaching A and landing in indeterminate form of 0 over 0. So this A was a finite number. Now suppose A is infinite. Okay. Then what do you do? In this case, introduce a new variable t, which is 1 over x. T approaches 0 from the right as x approaches infinity. You see, x approaches A. A is positive infinity. As x approaches positive infinity, t approaches 0 from the right. So my quotient functions fx over gx can now be written as f of 1 over t over g 1 over t. Now if I take, now you see this is now the finite case. So I may apply L'Hopital's rule for finite case, a equals 0. So when I take derivative, notice that gives me chain rule derivative. F prime of this times derivative of 1 over t. Upstairs and downstairs they cancel. So you get the same story as before. F prime 1 over t, but 1 over t is nothing but x. You see, that tells me 1 over t is x. So limit x approaching infinity fx over gx is limit x going to infinity f prime x over g prime x. Similar arguments can be used when a is negative infinity. Okay, so what happened here, we just saw indeterminate form of 0 over 0. But what about indeterminate form of infinity over infinity? Well, if f and g go both to infinity, then all you have to do is take reciprocal g over f. That will go to 0 over 0, because reciprocal of infinity is 0 essentially. So the argument follows simply from here. Okay. In other words, infinity over infinity can be rewritten in the form of 0 over 0, indeterminate form, and the proof of L'Hopital's rule continue. Here is a nice example. Find limit x approaching 3 of natural log of x minus 3. When x approaches 3, I should say from the positive side. Okay, otherwise the numerator doesn't make sense. Okay, pretend that's a plus. So x approaches 3, then x minus 2 approaches 1. X minus 2 approaches 1 from the right. Well, okay, I didn't have to. So sorry about that. 1, you can go from the right or left, it is okay. Natural log of 1 approaches 0. Okay, natural log of 1 is 0. So as x approaches 3, natural log of x minus 2 approaches natural log of 1, which is 0. As x approaches 3, x minus 3 approaches 0. So this fraction, this quotient function, its limit is indeterminate of the form 0 by 0. So we use L'Hopital's rule. Well, take the derivative of the top, take the derivative of the bottom. Now set x approach 3. That gives me 1. So limit is 1. We'll come to example 2 in our next video. Until then,